Okay, so remember what we did last time. Suppose that I have the graph of a function f of x. So we are looking at some function f of x in each of the four graphs. And so what do we mean when we say that the function f is increasing on an interval I? So let's say the interval I is from a to b. Okay. So the interval I is from a to b. So what does it mean to say that the function f is increasing on that interval? Well, in simple language, it means that the graph of f is going upward as you read the graph from left to right. Right? The graph of the function f is decreasing on the interval I. It means that if you read the graph from left to right, the graph is going downward. Right? What's the meaning of so in the first two graphs? Well, let me talk about concavity in a bit. So first of all, how do I say that the function is increasing in a little bit more mathematical way? Well, f is increasing on the interval I because given any x1 less than x2 inside of I, given any x1 less than x2 inside of I, f of x1 is less than f of x2, because that would mean that the height at x2 is bigger than the height at x1 for the graph, right? And f is decreasing on the interval I means that whenever x1 is less than x2, the f of x1 is bigger than f of x2, the opposite. Am I making sense? So notice that in both cases we are taking x1 less than x2. In one case, f of x1 is less than f of x2, but in the other case, f of x1 is bigger than f of x2. So for any pair x1, x2, whenever x1 is less than x2, f of x1 is less than f of x2, that would mean f is increasing on I. And whenever x1 less than x2 inside of I, it happens that f of x1 is bigger than f of x2, it means that the graph is going downward. Now, last time we also came up with an association between the increasing, decreasing behavior with the sign of the derivative, right? We said the function f is increasing or decreasing on I according as the sign of the derivative is positive or negative. So if if you look at any point on the first graph, you'll see that at any point on the first graph, the slope is positive. So that means that the derivative is positive. So if the derivative of a function is positive on an interval I, everywhere on the interval I, then the function is increasing on I. If the derivative of the function is negative for every point in the interval I, then the function is decreasing there. Right? Once again, f is increasing or decreasing on I according as the derivative is positive or negative. Okay? Now we have the concept of concavity. Concavity means that the first two graphs, we say that the function is concave up on I. Okay, so the function in the first graph is concave up on the interval I. The function in the second graph is concave up in the interval I. And then, if I look at the other two graphs, in the third graph, the function is concave down on I. In the fourth graph, the function is also concave down on I. Okay. Now, so if you look at the first picture, right, it's concave up. If I ask you, hey, which slope is bigger? Is the slope at x2 bigger than the slope at x1? Yeah, so what it means is that when the function is concave up, the graph is concave up means all the tangent lines are below the graph, Right? When I say a function f is concave up on an interval I, it means that all of the tangent lines lie below the graph. Okay? And also the slope of the curve is increasing as you go from left to right. The slope is increasing. If the slope is increasing, it means that the derivative is increasing. Am I making sense? Now, the derivative will be increasing according as the derivative is increasing if the second derivative is what? If the second derivative is positive, right? Because what's the derivative of f prime? The f prime function, the derivative of that is the second derivative, right? F double prime. So if f double prime is positive, that would imply that f prime is increasing. Am I making sense? If f double prime is positive on an interval I, it means that the derivative function is increasing on I, which would mean that the function is concave up. Am I making sense? In the second picture, it's the same thing happening, right? Is the slope increasing here? The slope is still increasing, because if you look at the slopes here, all the slopes are negative. So you have like negative and large slope here, and here it's becoming closer and closer to zero, right? So in fact the slope is still increasing here, but it's negative slope. That's why it's so the more flatter you are, the more closer the slope is to zero. And so here, the points here, the slope is bigger and negative. Okay. In the second picture, the slope is still increasing. Therefore, the derivative is increasing. F double prime is positive. Okay. So let me write that down. So far, what I said. So far, what we said is that in the first picture, f prime of x is positive for all x inside of I. In the second picture, f prime of x is negative for all x inside of I, right? All the slopes are negative in the second picture, so the function is decreasing. What can you say in the third picture? Is f prime positive? Is f prime positive in this third picture? Yes, it's positive for every x inside of that interval I. And in the fourth picture as well, the first derivative is now negative, right? All the slopes are negative now on that interval I. And in the third picture, what can you say about the slopes? The slope is decreasing, right? You realize that? In the third graph, which one has bigger slope? The point at x2 or the point at x1? The point at x1 has bigger slope. So in this third graph, the slope is decreasing. As you read the slope from left to right, the slope is decreasing, which means that the first derivative function is decreasing, and that would mean that the second derivative is what? That would mean that the second derivative is negative. Second derivative is in fact negative in this case, and that's why the function is what? The function is concave up. Sorry, concave. The function is concave down, and in the fourth picture, the function is still concave down, and so that means that the second derivative is what? Second derivative is negative here as well. Am I making sense? So second derivative is negative means that the first derivative function is decreasing, meaning that the slope is decreasing. And if the slope is decreasing on an interval I, it means that the function is concave down. Let's go up in this picture. In this picture, the function is what? Concave up here as well. And in both cases, what can I say about the second derivative? The second derivative is what? Positive, because the slope is increasing. Same thing here, the second derivative is positive. Is everybody okay with that? So if I ask you determine where if given function is concave up and down, what would you do? You'll find the second derivative and you'll determine where the second derivative is positive and negative. Am I making sense? Is everybody okay? Okay, so are all these pictures clear to you? Any questions? Okay. Here's an example. I'll start with something easier and then we'll look at what type of problems you should expect in the exam. Let's say I have the function f of x, which is x to the 2/3. I think last time we looked at the example of x to the 1/3. The question here is the same. Determine where the function f is increasing and where f is decreasing. And the second question is determine where the function is concave up and where the function is concave down. Is that clear? So that's the question that I want to answer. And so what should I do? Well, the first thing that I need to do is, first of all, I'll say that the domain of that function is what? The domain is what? All real numbers. And okay, so the first thing I do is compute the derivative. So if I look at the derivative of f at x, that will be the power rule, 2/3 x to the what? Negative 1/3, which is the same as 2/3 times x to the 1/3. Okay, now I have to determine where the function, where the derivative is 0 or doesn't exist. Okay, so in order to find where the function is increasing and where the function is decreasing, this is my first step to finding where the function is increasing and decreasing. And then the second step would be that you want to solve f prime of x equals to 0 and solve f prime of x does not exist. Okay, for x in the domain of the function. Well, what did you say here? In this case, the derivative can never be 0, right? Because the derivative is 2 divided by something, and the numerator is not 0, so it couldn't be 0. And so the only place where the derivative doesn't exist is where? 0. When x is 0, the derivative doesn't exist. So these are the critical points of the function f, right? These are the critical points of the function f. These are the points where the derivative is either 0 or doesn't exist. Once I have those numbers, I am going to plot the domain. So let's plot the domain here. So domain is all real numbers. Once I have drawn the domain on the real number line, I am going to plot. So this is the third step, okay? Third step. You plot the points where the derivative is either 0 or does not exist. So the only point that we found was 0. Once you plot this point on the domain, you see that the domain is being divided into two parts: negative infinity to 0, 0 to infinity. On each part, you have to decide what's the sign of the derivative function. So let's look at the derivative function. On the right side of 0, it means that if x is on the right side of 0, it means that x is positive. So when x is positive, is the derivative positive or negative? When x is positive, is the derivative positive or negative? What's that? When x is positive, if you look at the derivative function, right? Is the derivative function positive or negative? Positive. And when x is negative, when x is on the right side or on the left side of 0, what's the sign? Negative, yes. So we see that the derivative f prime is negative on the left side of 0 and positive on the right side of 0. So what does that mean? It means that the function f is decreasing where? The function f is decreasing on the left side of 0, and it is increasing on the right side of 0, right? So f is decreasing here, and f is increasing on the right side of 0. Is everybody okay? You guys are okay with that? How would I write it? Well, the way I would write it as my answer is that f is increasing. So I'm going to just write this symbol. It means that f is increasing on 0 to infinity, and f is decreasing on negative infinity to 0. That's how I will write my answer. If the question is find where the function is increasing and where the function is decreasing. Is everybody okay with that? So the function is increasing on an interval according as the derivative is positive or negative, right? Okay, now we want to decide where the function is concave up and down. So what do I do for that? How do I determine concavity? Well, the first thing I need to do is find the second derivative. And the second derivative, in this case, what was the first derivative? It was 2/3, actually negative 1/3, right? So what's the second derivative? What's the second derivative? Negative 2/9. Actually what? Negative 1/3 minus 1 is what? Negative 4/3, which is negative 2 over... Is everybody okay with the derivative? You're just applying the power rule, right? Actually 4/3. And then, once I know the derivative, what should I do? I have to solve f double prime of x equals to 0 and solve f double prime of x does not exist for x in the domain of f. So solve these two, and in this case, once again, I look at the formula for the second derivative. I see that the second derivative cannot be 0, right? Because you're dividing 2 by something, and you can never end up with 0 when you divide 2 by something. So the only solution here I get is that the second derivative does not exist where? The second derivative doesn't exist when x is 0. And okay, so once again I do the same thing as I did before. I guess I could do it in the same picture if I wanted to, okay? That is, let me use a red pen here. after that you want to, so you plot the, oh maybe I should do it separately, okay. So sometimes the points are different. So let's say I have the number line again. I plot the points where the second derivative is 0 or does not exist, which is 0. 0 divides the domain into two parts. I need to decide what is the sign of the second derivative function in each part. I look at the second derivative function. When x is larger than 0, when x is on the right side of 0, what can you say about the sign of the second derivative? It will be negative. Negative here. So I'm looking at the sign of the second derivative. And what can you say about the sign of the second derivative on the left side of 0? The denominator you have x to the 4/3, right? Because of that 4, it's actually x. So x to the 4/3 is in fact the same as x to the 1/3 to the 4. You need to realize that. And once you realize that, then you know that the denominator is always positive, even if x is negative or positive, right? So that means I still get what? I still get the second derivative is negative here. Is everybody okay with that? Okay. So what do I see? I see that the graph, the second derivative is concave down on the left side of 0. It is also concave down. So here I'm saying f is concave down on the left of 0, concave down on the right of 0 as well. And let me in fact show you how the graph of this function looks like. Here's the x-axis, here's the y-axis. Remember what we said, on the left side of 0 the function is decreasing. Now we know it's concave what? So on the left side of 0 it's decreasing and concave down. On the right side of 0 it's increasing and concave down still, right? So how will the graph look like? By the way, the function was actually what? 2/3, right? When x is big, what do you expect actually the 2/3 to be? Big, right? When x goes to infinity, actually 2/3 goes to infinity. When x goes to negative infinity, what can you say about actually 2/3? It still goes to infinity because actually 2/3 is actually 1/3 squared. So actually 2/3 is always positive. The function is actually 2/3, and actually 2/3 is always positive, right? So when x goes to negative infinity, the function actually goes to infinity. So my point is, the function is going to come from positive infinity, and it's decreasing, and it is decreasing and concave down, right? So wouldn't that how it looks like? So at 0, the value of the function is 0, right? At 0, the value of the function is 0. So I know that on the left side of 0, the graph is concave down like this, and it's decreasing. And on the right side of 0, the function is concave down still, but it's increasing, and it's going to infinity, so it should look like this, right? Am I making sense? So the point, though, I only plotted one point. Which point did I plot? I only plotted one point at 0, right? Why? Because 0 was the only solutions I got when I looked at where the derivative is 0 or doesn't exist, where the second derivative is 0 or doesn't exist, right? Those are the critical points, and all I need to do is plot the critical points and then use the information about increasing, decreasing behavior and concavity to draw the curve. Am I making sense? One thing I needed here was that I needed to know whether the function goes to infinity as x goes to infinity. Why? Because if I didn't know that, then I don't know. Maybe the curve is, maybe there is a horizontal asymptote and the graph looks like this. Am I making sense? So I need to know the behavior of the function as x goes to infinity. Otherwise, I'm not exactly sure how the curve behaves for big X, right? Is everybody okay with that? All right. Again, we'll see more examples as we go. Okay, so that's how we can draw the graph here. Now, in the exam, I wouldn't be asking that easy. I'm not going to give you that easy functions like this. I'll give you a little bit more complicated function, but not that much. So I'll give you some examples in a bit. Let's do one more easy example. If I have the function g of x to be x to the 5, right? How would I determine where the function is concave up and down and where the function is increasing or decreasing? I will have to find the first derivative, which is 5x to the 4, and I will also find the second derivative, which is what, 20x to the what, 3. What's the domain of this function? All real numbers, polynomial function. So now I'm going to plot the points where the second derivative is. So let's plot the points where the first derivative is 0 or does not exist. Can someone tell me where this first derivative is 0 or doesn't exist? Yeah, when x is 0, the first derivative is 0, and the first derivative is defined everywhere. The second derivative, same case, right? The second derivative is 0 exactly when x is 0. Otherwise, the second derivative is defined. So I get only one critical point. And then what I do is come up with the sign of the derivative. So let's see. So what's the sign of the derivative g prime? When x is positive, what can you say of the sign? What can you say about the sign of g prime? It's positive here, and is it positive here as well? Because when x is negative, actually 4 is still positive. So I know that g prime is positive throughout. What can I say about g double prime? When x is positive, is g double prime positive? Yes, x cubed would be positive, right? When x is negative, g double prime would be what? Negative, because x cubed would be negative when x is negative. So I get negative, 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 negative. And so what can we say finally about the function g? The function g is increasing here, right? It is in fact it's increasing throughout, right? So let me actually first of all say that this is concave down here and concave up here, because the second derivative is positive, negative and positive, and then I will say that the function is in fact increasing throughout, right? The function is increasing throughout. Is everybody okay with that? And what's the graph? Well, we already know the graph of actually 5. I'm just trying to show you that indeed we get the same graph as we saw before. And the graph would be like, remember, it is concave up on the right side of 0, concave down on the right side of 0, right? Concave down on the right side of 0, and it is at 0 the value is 0, and it is increasing throughout, right? That's what we found out. It's increasing throughout. It's concave down on the left of 0, concave up on the right side of 0. Is that okay? Okay. Now, an example which is more like a exam problem. So let's say I have f of x is equal to 3x to the 4 minus 4x cubed minus 12x squared plus 5. So let's say I have this function, and again the same question. Determine where the function is increasing and where the function is decreasing. Determine where the function is concave up and where the function is concave down. So what do? Well, first of all, let's write down the domain. And again, it's a polynomial function, so I don't even feel like asking that question. So this is the domain. And what's the first derivative? The first derivative is what? 12x cubed minus 12x squared minus, what is that? 24x. Okay, and let's also find out the second derivative at the same time. The second derivative would be what? 36x squared minus what? 24x minus 24. Okay, so now we solve. So let me just say I have done 1 and 2 and 3. I want to find solve f prime of x is 0 or does not exist. Sorry. Let's just solve this for x in the domain of f. Because the first derivative is defined everywhere, so we know that you cannot find any value of x where the first derivative doesn't exist. So how do I solve it? Well, this is what? 12 x cubed minus 12x squared minus 24x equals to 0. And then if I factor out 12x, I get x squared minus x minus what? Minus 2, right? Is everybody okay? Usually in the exam I see people making mistake right here when they try to solve for this equation. Now, how do you factor that out? X minus 2, x plus 1, very good. And so what do we get? We get x is 0, x is 2, x is negative 1, and they are all in the domain of f, right? Okay. And now that I have these points, I can remember the first derivative is defined everywhere, so I don't have to worry about finding x where the derivative doesn't exist here, right? Is everybody okay? All right. So now I plot the. This is the domain, everything, right? All real numbers, and then I plot the critical points I obtained. So negative 1, 0, and 2, right? These are the critical points. And what do I do now? These 3 points divided the domain into how many parts? 4 parts. Negative infinity to negative 1, negative 1 to 0, 0 to 2, 2 to infinity. And on each part, you have to decide what's the sign of the derivative function. So let's look at the derivative function. Remember, the left-hand side of my equation here was the derivative function. You realize that? I didn't divide out or do anything with the derivative, right? So the derivative function, remember, was this is the derivative function, right? So, and I factored it out. And I got this. So this is my f prime, right? So can someone tell me what's the sign of the derivative when x is less than -1. For example, plug in -2 there and see what's the sign. So when x is less than -1, the first factor x is negative, right? When x is less than -1, the second factor is what? Negative. When x is less than -1, the third factor is negative. So 3 negative gives you a negative, right? So negative, 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 negative. Between -1 and 0, when x is between -1 and 0, what can you say about x plus 1? Positive. For example, plug in -half. So when x is between -1 and 0, x plus 1 is positive. X minus 2 is still negative, and x is still negative. So you have 2 negative factors and 1 positive factor, right? Do I get plus then? Okay, between 0 and 2. When x is between 0 and 2, the first factor x is positive. The second factor is going to become negative. X minus 2 would be negative. And then x plus 1 is positive, right? So 2 positive, 1 negative. Negative, 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 negative. If you don't like this, you can plug in a number from that interval. So if between 0 and 2, I can plug in 1. So plug in 1 for x and see what sign you get. Is that okay? And if x is larger than 2, the first factor 12x would be positive when x is larger than 2. When x is larger than 2, x minus 2 would be positive. When x is larger than 2, x plus 1 would be positive. So positive, positive, positive would be all plus here. So now this is so these are the signs of the first derivative. So now I see that my function f is decreasing here, increasing here, decreasing here, increasing here. Is that making sense? You guys are okay with that? Okay. Now we have to determine where the second derivative is 0 or does not exist. Okay. So this is, I guess, which I forgot what number I'm using here. 3, 4. So solve the second derivative equals to 0. Remember, we already know that the second derivative is defined everywhere because it's just a polynomial. Now, second derivative was what? What was the second derivative? You have it in front of you? The second derivative is what? Say it again. 36x squared minus 24x minus 24 equals to 0. Okay, now I can factor out what? What can I factor out? If I factor out 12, what do I get? 3x squared minus 2x minus 2, right? Is everybody okay with that? Are they both negative? Yes, they are both negative. Okay, so now how do I solve this? Well, the best thing to do here is just to apply the quadratic formula, right? So from this, you know that 3x squared minus 2x minus 2 would be 0. So by the quadratic formula, what is x? What is x by the quadratic formula? Minus 2, right? That's the minus negative of the coefficient of x plus or minus square root of b squared would be negative 2 squared minus 4 times the coefficient of x squared is 3 times the constant term divided by what? 2 times the coefficient of x squared is 3. Everybody's okay? That's what you get if you apply the quadratic formula, and we have to simplify that. And if we simplify that, we would be getting 2 plus or minus root of 28 divided by 6. And so this would be the same as 2 plus or minus. The root of 28 means 4 times 7, right? And the root of 4 times 7 would be 2 plus or minus 2 times root 7 divided by 6. And we can cancel out a factor of 2, which would give me 1 plus or minus root of 7 divided by 3. Is root of 7 bigger than 1 or bigger than less than 1? Root of 7 is bigger than root of 4, which is 2, so it's bigger than 1. So I know that if I take plus, I get a positive one. If I take negative, I get a negative solution. Okay, so these are the only two places where the second derivative is 0, and we know that the second derivative is defined everywhere. So once again, we draw the real number line, and we draw the domain of the function. The domain is everything, and now we plot the places where the second derivative is 0 or it doesn't exist. So here, one point is what? 1 minus root of 7 divided by 3. The other point is 1 plus root of 7 divided by 3. In fact, I know that one of them is negative, the other one is positive. So I know that they are on opposite sides of 0, right? But I don't need to plot the 0 in this case, okay? 0 is not a place where the second derivative is 0 or doesn't exist. So now, the second derivative, I need to know where the second derivative is positive and negative. Is that clear? So look at the second derivative function. Now, can someone give me a number on the left side of 1 minus root 7 over 3? Yeah, it is, just take, for example, if 7 is 9, for example, then you'll be on the left side of that, okay? So, for example, if I take 9 there, you get negative 2/3, so negative 1 is in fact on the left side of that. You realize that? Negative 1 is on the left side of this number. You can use the calculator, or this number is bigger than, if I plug in 947 here, would that number be here? If I replace this expression, the root 7 by root 9, that number would be on the left side here, right? Because I'm subtracting a bigger number. So what is 1 minus root of 9? That's 1 minus 3, which would be negative 2/3. So negative 2/3 is right here. Therefore, negative 1 is there. So you can just plug in negative 1. So plug in negative 1 in the formula for the second derivative. This is the second derivative, right? So here, if you plug in x equals to negative 1, what did you get? You realize that? You're going to get positive. So I know that it's positive here. Okay, now, between 1 minus root 7 over 3 and 1 plus root 7 over 3, the number 0 is there, right? So plug in 0 for the second derivative. So if I plug in 0 for the second derivative, what do I get? I get negative 24, right? So I know that if I plug in that, I get negative throughout here. And what would be a number bigger than 1 plus root 7 over 3? Well, if I plug in 9 for 7, I get 1 plus 3 over 3, which is 4/3. So 4/3 is on the right side of that. Instead of taking 4/3, let's pick something nicer, which would be 2. So plug in 2. Plug in 2 for the second derivative formula. 36x squared minus 24x minus 24. If I plug in 2 there, I am going to get what? Yeah. So what's going to happen now? Well, we know that the function f would be concave down here, concave up in between. Oops. Thank you. So this would be concave up here, concave down here, and concave up here. Is everybody okay with that? Okay. The last thing that I wanted to do was show you the graph of that, but why don't you guys come up with the graph of that yourself, and then next time you can check with my answer. But before that, in order to draw the graph of this function, you need to decide two things. Remember, the domain is from negative infinity to positive infinity, so you need to know the terminal behavior of the function, meaning that what's the limit of the function as x goes to infinity, and you also need to know what's the limit of the function at negative infinity. And in both cases, remember, what is the leading term in my function? My function is a polynomial function, and the leading term is what? No, the leading term was 12. I think it was actually 4 multiplied by what? 3x to the 4. What is happening to that as x goes to infinity? It goes to infinity. It still goes to infinity when x goes to negative infinity. So in both, terminal behavior is that the graph is going upward forever in the terminal cases. So knowing this, the way you want to plot this graph is that you should plot the points on the graph corresponding to the x values that we obtained. Remember, there were 3 x values where the first derivative is 0. There are 2 x values where the second derivative is 0, right? 5 of them. You must plot those 5 points first. Use your calculator to approximate the y values. Okay? You plot those points and then decide, then look at the increasing, decreasing behavior and concavity behavior to come up with the graph of the function. Okay? So you should do that as an exercise, and next time you can match with my answer. What's that?
Will you be in your office this afternoon?
Yeah, what time?
Around 4.
Yeah.